So actually today we are going to start up with the Linux internals, right? So before starting our device drivers, we have to actually complete this Linux internal that will give you an overview of the API to the kernel layer, right? How we interact with the system calls to the kernel layer. So
Okay.
So these actually are the content for all the Linux internal process. So actually these all are not covered in today's session, but we will actually complete this in the I think we can complete it in the next session. So these are actually the components. So first one is the system calls. We'll study about what system call is and what are the system call, how they work. So then we have process, then we have the IPC mechanism that we use in the Linux, then we have the signals, then we have the networking aspect of our Linux, then we have the threads, then synchronization, then we have the process management, how the kernel actually process this handles the processes, and the memory management. So let's start. So there are a few questions. What exactly is operating system are? What we need for an OS? How do an OS would look like? So is it possible to team us with to create a OS of its own? Is it necessary to have OS in the embedded system? Will the OS ever stop at all? So these are the few questions that we have in our mind before starting of the Linux system. So we'll cover these all things, and you will get to know how these all things work. So this I think I have already discussed. Like we have the hardware, we have the OS layer. On the top of that, we have the application. So the same thing is here. So why we need an OS? So it's actually used for a multitasking and multi-user and scheduling and the memory management. So you see a girl actually is handling the baby and all the things all together. So actually, this is something called as a multitasking, right? So
Okay.
right, so this also we have discussed, I think, in the last session, right?
Yeah.
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 Okay, so we'll
Both in
skip.
segments.
Yeah, yeah. So we can skip that. So this is a control for of an OS. So this is an operating system modules. So it resides in the kernel layer, and that also actually permitted by the supervisor mode. So we have the root permissions for this modules to actually access this. So here we are just booting our OS, we are just calling the main, that this main will actually initialize. So we have seen the flow of a kernel using start underscore kernel function in the kernel source, right? So the same thing is actually showing here. So on the top of that, how this operating system modules is being handled. So this is through the interrupts, this is through the system call, this is through the exception. So this is a user mode, and there is an interface between the user mode, right? So this is small history. So we have a vertical and horizontal aspect of this. So we will see what it is. Actually, we have discussed this history also earlier also. So here is a vertical one. So vertical is before 1970. So in vertical, hardware and software made by the same company. OS is integrated part of the hardware, and application were proprietaries. So this is actually the monopoly of the companies to actually sell their hardware with the interfacing also. So we have to take the hardware and we have to take the interfaces of the same company, right? So in the horizontal approach, hardware and software made by the different company. So actually that increased our selling market of interfaces. So we have the different company hardwares that can interface with each other through some layers. So this is, I think, this is a somewhere. So how does OS look like? So it is a hardware only, software or hardware. So it's a software and a hardware. So how big is the OS? So it can range from a KBs to the MBs or to the GBs also. So it depends on what are the modules you are taking into the OS. So the all the packages, all the software that you have installed. So that is the main. So So this is some small diagram. So here we have some hardwares, and on the top there is operating system. Then we have the system and the application programs. Then we have the compiler, assembler, text, and all the things. So this is, I think, this is covered. So this is communication message passing. So most older operating system are monolithic. So this is now we are going to the classification of a kernel. So as I told you earlier, there are two types of actually classification: monolithic and microlithic. So most older operating system are monolithic. That is, the whole operating system is a single executable file that runs in the kernel mode. So we have all the device drivers that will be running onto the same executable. So this binary contains the process management, memory management, and file management, and the rest. So this we have already discussed. So because of our Linux, we have a monolithic kernel. So they all the components are actually in the kernel layer. So the alternative is microkernel based system, in which the most of the OS run on a separate process, mostly outside the kernel. So they communicate by message passing. So this also we have discussed about the microkernel. So we have a minimum device drivers or minimum components in the kernel layer, and rest we have on the application layer, and they will interact with each other using some system APIs. So they communicate by message passing. The kernel job is to handle the message passing, interrupt handling, low level process management, and possibly the. So this is actually the architecture view of both the classification of the kernels that we have used. So this is a monolithic kernel, right? So here what are the differences between the two? So you see here there is a line between this and this. So these all the components in the monolithic kernel are in the kernel mode, and in the monolithic microlithic kernel we have this small part is running in the kernel mode, and all the device drivers, file servers, Unix servers, and application are running on the top of that. So they are interacting with each other through the interface. So here we have a large bunch of layers in the kernel mode. So we have the virtual file system, we have the IPC file system, schedulers, virtual memory, device driver, and dispatcher all are in the kernel mode. So I think this is clear, right?
Yeah, yeah, it's clear.
Okay. Okay, right. So let's go the difference between the two. So monolithic kernel size increase because the kernel and the kernel subsystem compiled in a same single binary. So in the kernel size is small because the kernel subsystem run on the separate binaries. So difficult to extend or bug fixing because we have all the components of the kernel in the same layer. So it is very difficult for us, because if any module will get corrupted, the whole OS will crash. So you will have this problem when we load our kernel and we have some problem in our device driver when while loading, then the kernel will get crash and code dump will be produced. So this is a problem in the monolithic kernel, and in the microlithic kernel easily extendable and bug fixing. You need to compile the entire source code. So here we have to compile the whole source code, and it takes a lot of time. It depends on the system. It will take up to 3 to 4 hours also. So easily recover from crash and bad maintenance. Then we have slower use of complex message passing between the services. So the monolithic, it is faster because all the components that is intact into the same kernel layer. But in here, process management is complex because the processes management is running on the outside the kernel layer. So communication between the services is fast, and communication is slow because we have all the softwares that are device drivers that are running on the top of a kernel layer. So communication is slow, right? So no crash recovery, easily recover from crash. We have the Windows and a Linux extra. It is a monolithic kernel, and in the Mac OS and WinNT, we have the microlithic kernel. So here we have the same thing. Oh, we are doing it again and again. We have hardware, device drivers, kernel, system APIs, and application. So now coming to the C perspective. So C have the algorithm, syntax, and logic. So there are various stage of compilation of a C program. So we have a preprocessor stage, we have the compiler stage, we have the assembler state, we have the linker state, and we have the executable file. And OS has a memory segment, process threads, signals, IPC, and networking. So it executes the program and load onto the RAM. So it's the actually the application of a OS layer to load this A dot out onto the RAM, right? So this is the application programming compilation stage. So the first one is a preprocessor stage. It expands the header files, substitute all macros, remove all comments, expand all hash directives. Then we have a compilation stage, convert the assembly level instructions, and then we have the assembly state, convert to machine language instruction, commonly called as an object file. So when we go for an object file, then the last stage is the linking stage, in which all the object file are being linked together to create an executable. So linking with the library is also there in the linking stage. It may be your static library or a dynamic content. So this
Okay.
is a compilation stage. So in the pre-processor stage, when we have this command, so you actually try with GCC ever to work on GCC? You have to
Yeah.
compile the C program, right? Okay,
Yeah.
so this is a command that this file.c, and it will save all the temporary files into the same folder, and it will generate the intermediate files. So first stage is .c that contain the source code, compiler state .i that expand the code, gcc-e. We can use this command also in spite of this, because it will save all the intermediate files. But if you want to take out the actually the particular file, then we have to use this option with GCC. So this is the assembler source code, the gcc-s file.c. Then we have the linker .o files. These are the object file, and these are compiled by this. And then last is a loader, and it will give us our a.out. That is a default executable name in the Linux if you're not giving any name to the compile executable, right? So now comes the static linking. So static linking is a process of copying all library modules using the program into the final executable image. This is performed by linking and is done as a last step of the compilation stage. So compiling two .o files also type of static linking. To create a static library, first create the intermediate files, and this is actually the command which is used to actually create the library for static library. So create two object files, fun1.o and fun2.o, then creates a library. So this is a command to create the library, static library in Linux. So we can use AR with RCS. Then we have the library name, and then we are giving the input as a two object file. So have you ever tried for static linking, static
Yeah.
libraries? Okay.
Also dynamic and static.
Okay, right. That will be fine then. So it will perform the linking process when programs are executable in the system. During dynamic linking, the name of the shared library placed in the final executable file. So actually, linking take place at runtime when both the executable file and libraries are placed in the memory. So the main advantage of a dynamic linked library is that the size of the executable is reduced. So we have all the dynamic libraries in the system, so they can take advantage. But if we want some porting of the app, then it creates a problem if you don't have the library in that system, right? So to create a dynamic library, shared library is used. So here is a simple GCC command. Here we are using libfun.so file, that is a dynamic linking, that dynamic library that we are using here. So next is a this is a static versus dynamic. So executable file size will increase in a static, and in a dynamic it will decrease. Loading time will decrease, and here it will increase. Then we have the memory uses that will increase in the static, and it will decrease in the dynamic. So number of system call will decrease, and here the system call will increase because the executable have to get the data from a kernel layer. So that's why it's doing here. So now comes the process, the running state of an executable. So this is a RAM. We have a list of processes that are running onto this RAM. So this is actually the memory layout. So earlier we have studied about the C compilation stage, and when that a dot out is created, then when we launch that a dot out, then it comes into the memory layout view. So this is the memory layout view of a process. Uh, right, so we have this code segment here in the below section. Then it contains the source code of a C file that we have created. Then we have the initialize and BSS segment. Then this is called the data segment. It contains all the global variables that are defined into your C program. Then we have a heap segment. Here we are locked in a memory by using malloc, alloc, and other things. So it is going upward, so heap will increase upward. And here we have the stack. It is a local stack that is local to your function. Right, so we have a hierarchy of a stack while loading this process, so it will go downward, right? And here we have the command line arguments, so it will reside in this. So this is a stack frame. Here we have the local variables, return address, parameter list.
Okay.
So here's the storage class, some storage class, auto, register, static global. Then we have extern. I think you know these commands, right?
Yeah.
Okay, so we'll skip that. So you can try this also. So common errors while we are dealing with the process. So in the stack segment, there is one called as a stack overflow. When this memory actually is less and the stack values are more, so sometimes we actually create some recursive process and we actually forget to actually write a end loop. So in that case, the infinite times it will run, and when it get overflow, it will give you a stack overflow error. So you ever have actually got this error, Stack
No,
Overflow?
I haven't.
Okay, so you try one recursion function and you just call this function within that function. So you have some local variable into that, and when you run that program, it will crash and give you an error of Stack Overflow that will be shown on your command line, right? So you can try that also. So this is a heap segment and this is a memory leak. So when there is a memory leak, so if we have so you ever use a malloc or calloc?
Yeah.
Okay, so if you alloc some memory and you don't free that memory, right, while using it, so that pointer actually points to that address only, right? So if you don't free that memory, then it will be a memory leak, because according to the process, it is a used memory. So we have to free the memory once we have created it. So when you never free a memory after allocating, eventually process heap will run out. So there is one more error that is called as a segmentation error. When you try to change the text segment, which is read-only memory, and try to access a memory beyond the process memory limits, like null pointer. So these will give you some error of a segmentation fault.
Yeah. Yeah.
So any question till now?
No, no, everything
Okay.
is okay.
It's simple, right? So Linux is free and open source that is causing revolution in the computer world. Originally created by Linux Torvald, this operating system is a few short years in the beginning to dominate the market. So free and open source, GPL license, no cost, reliable, build system with 99 point upstream. Then we have the secure, monolithic, offering high security, scalable, because for a mobile market, small embedded devices. So these are the components. I think we have discussed these, right?
Yeah.
Okay, so let's skip that. This also, I think we have discussed in the previous, right?
Yeah, in the previous session.
Yeah, this is done, right? So now this is a virtual file system. So here we have the drivers and the buffer cache. Then we have this ext file system, ext3 file system. Then we have slash proc. So we have discussed that all the processes in the running state will have an entry in slash proc. depending on their PID number. So here we have files and pipes and FIFOs, that is IPC mechanism, and sockets also there for the IPC mechanism. And on the top of that, there is a virtual file system or a Dentries inode. So this actually is every file in a Linux. Sorry, every data in the file. Sorry, it's a every data in the OS is a inode. So every file in the file system have is inode value. So Dentry. So Dentry is for directory structure. So every directory also have their inode value, and also they actually cache some value, so for the faster access of a file, right? So these two terms are being used in the Linux in the virtual file system. So on the top of a virtual file system, we have the system call interface. So this is very important interface. Actually, it's a interface between the user processes and the kernel. So if we want to access some kernel functionality, so we can use this system called interface in our C program to actually access the data from the kernel layer. So present the user with a unified interface via the file related system call. The VFS, virtual file system, interact with the file system, which interact with the buffer cache and page cache and the block devices. So VFS actually is actually related to some buffer cache also, and they will interact with these all cache, and that helps in faster operation in the file system. Finally, the VFS supplies data structures such as the dcache, inode cache, and the open file tables. So allotted a free file descriptor, try to open the file. On success, put a new file structure file in the FD table. So the file descriptor table is there of a process, so it will actually put that file in a that process. So on error, free is locking by the file descriptor. So VFS make everything is file in Linux. So it's actually this code here. So this is actually the summary for this last slide. So this is compilation state, storage state. Then we have the program process. On the top of that, there is a Linux internals, and there is a going to the Linux device drivers.
Okay.
So now we are going for a system call. So there are two types of communication, and one is a synchronous and one is a asynchronous. So in a synchronous uh, type, we actually work in the polling mechanism, in which the master and the slave both actually interact with each other depending on some time, so that they can sync up their clock or some other data. So that is called as a synchronous communication. So in asynchronous, we don't know what is coming to us, so it will actually generate the interrupt first, then this process will handle that. So this is actually the, you know about the difference between synchronous and asynchronous.
Um,
Yeah.
yeah, well, at least I know what is an interrupt.
Okay.
About
Okay.
pooling, it is I/O control calls from user
Yes.
space. Okay. And interrupts
uh,
are drive by hardware, right?
yes, but interrupts actually are the two types. Further, we have the software interrupts and the hardware interrupts. So depending on that, we will work on that. But in a synchronous mechanism, so there is some like we have some master and the slave. We have two device, master and the slave, and they have their different clock cycle. So sometimes we do one thing, we just want to synchronize that process, so that clock has to be synchronized. So we actually poll that hardware, so that we will match the clock of both the hardwares, so that there is a fast communication between the two. So that is one of the case we are using this synchronous communication. And rest we can actually have the TCP handshaking. So that is also used for a synchronization communication, so that the data will go fast, right? So
Okay.
that is the main actually. So interrupts, right? Here it is. Interrupts are two types, hardware and the software. so generates whenever a hardware changes happens. So it's a IO, right? You said earlier. So it's a type of a hardware interrupt. So in generate by the instruction from the code. So it can be actually generated by the code. Like we have a signal system call actually that works on the software interrupt, right? So interrupts control signals CPU that interrupts had occur past interrupt number. So we have different interrupt numbers in the kernel. So we can have that number like hyphen 9 8 up to various number. So we can use that and generate the signal and do some processing. So basic program state saves user interrupt number to determine which handle to start. Then we have the CPU jumps to the interrupt handler. When interrupt done, program state reloaded and the program resumes. So that is a main actually action that is performed in case of a interrupt. So we have the some ISR interrupt service routines that is being called when we have an interrupt, right?
Okay.
So, system call a set of interface to interact with a hardware device such as the CPU, disk, and printers. So we have a various advantages of having the system call, freeing user from studying the low-level programming because system call are somewhat the wrapper above the kernel to interface with the kernel level APIs. So it actually decrease the complexity because we have a more complex operation in the kernel, like we use a print call, right? So it is accessing the kernel space to write on a std out. So there is a long operation of a printf, but what sees to us is just go and just put a string into the printf and it will print. So that is actually the power of having these small operations, right? To increase system security, these interface make the program more portable. So main thing is a portability. So we are actually resolving the APIs for the OS so that it can be ported on another hardware also, depending on the architecture, right? So if you don't
Okay.
have that architecture, it will not run on that. But if you have the same architecture and a different board, then it will definitely run on that board. So for a OS programmer, calling a system call is no different from a normal function, but the way system call is executed is very different, right? So here is a small system call open we are using here. So actually open will actually open a file and returns a file descriptor, right? So here is a user application and we are writing a code and in which we have actually use a open system call. So what it does when the code comes into the open system call, it will go to the system call interface. So when it goes into the system call interface, now the next point they have to actually uh, use the kernel mode APIs recursively. So open is implemented of open system call and it will return. So once this operation in the kernel space is complete, it will return some value to this system call interface, and this system call interface then in further give it to the user application. So that's why we get the file descriptor that is returned from the kernel layer, not from the user mode. So that is the whole process, but this process is so fast that it will actually have a actually just a blink of a second we can get that, right? So that is the power of a Linux kernel actually. So here is the call sequence. Okay, so first there is a user task. So user task executing, then it will call the system call. Then once it calls the system call, it will generate a trap. So here is a trap and it will set the mode bit to 0. So when it set the mode bit to the 0, it means this trap is handled by the kernel layer. So once it goes into kernel APIs, then it will execute the system call and return, and then it will put the mode bit to 1, that designed that it is for the user mode. So it will return from the system call. So logically the system call and a regular input follows the same flow of the steps. Sources, I/O devices, whereas user program is very different from both of them. Since call is generated by the user program, they are called as a software interrupts or traps. So a library
Okay.
function is an ordinary function that resides in the library external to your program. A call to the library function just like any other function call. A system call is implemented in the Linux kernel and specified procedure is required to transfer the control to the kernel. Usually the each system call has a corresponding wrapper routine, so which define the API that the application program should embed. So understand the difference between function, library function, and the system call. So you should think of these three terms, and you can actually differentiate between them. What are the difference between these things? So that is actually the very important thing from the programmer perspective. There is nothing but the simple C function. So So this is some implementation of a system call. Here we exercise that we have some code in the user mode, and it will actually jump to the system call kernel mode. Then it will execute some statements. Then it will return, and this is a service call routine. So system call handler is there. So it is like just like that. There is some like we have a trap interrupt. So it will actually call this system call handler, and it will return something. So it also work on a interrupt mode, right?
Okay.
So, so there are example of a get time of the day, get the system clock time, right? It takes a pointer to the struct time wall variable. So if you ever use this this API, you will know that this is a structure that is handled by the kernel layer, and it will put on, if you put some values onto this structure, it will be shared with the kernel and take that and give the desired result. So there are two parameters of this structured time well. There are TV underscore sec that designed for seconds, and TV underscore microsecond that is used for a microsecond. So if you fill these values into this structure and just call this API, then it will actually send this structure variables to the kernel and give you a defined time delay, right?
Okay.
Also, right? So a high precision version of a standard Unix sleep call. Instead of sleeping an integer number of seconds, nano sleep, because in a kernel layer we don't want our program or a driver to hang for a lot of seconds. So we can use this nano sleep in that scenario also, but we cannot use this sleep function into the ISR, because it will create a problem, because the main function of the ISR is just a click of a second, right? We cannot have, we have the nanoseconds for a process of a ISR, so we cannot use the sleep function into the ISRs. So take an argument of a pointer to a structured time-well object, which is expressed to the nanosecond precision. So here is a nanosecond. So these are the list of system call. There are many more to that, but these are open, read, write, exit, close, wait for a PID, get PID of a process, sync, and nice. We can change the nice value also. So there is one more that is a signal generator. We call it a signal generator. That is a kill command. So you can kill any process. You can actually pause any process. You can actually continue a process. So it's all done by this kill command, and kill and plus this signal number. You have to give the signal number to the kill to fire on a particular process. So this is called as a process management. So
Okay.
let's start this process again, because that is the main constituent of this OS. So everything is a process because it's running in the RAM. So running instance of a process is called a process. So if we have two terminal windows showing on the screen, then you're probably running the same terminal program twice and have the two terminal process. So these are the two terminal process. Probably running a shell. Each running shell is another process. So when you invoke a command from the shell, program is executed in a new process. The shell process resumes when the process completes. So we have a difference between a process versus a program. So a program is a passive entry, such as a file containing a list of instructions stored on a disk. Process is an active entity which, with a program counter, specify the next instruction to execute and a set of associated resources. A program becomes a process when the executor file is loaded onto the main memory. So we have a dot out. When we go to the shell and type dot slash a dot out, it will actually created a process. So here are the factors: storage state, dynamic memory, then we have the active state, then have a secondary memory. So this is a program. When it load, it goes into this section. Then we have various details that we have already discussed regarding this process. So more processes memory. So we have a list of processes in our RAM. So each process have its own code, data, heap, and stack. So that is more important actually. Every process have its own memory segment, right? That is running onto the RAM. So we have some free space between them also to actually distinguish between the two process by the processors. So this, I think we have discussed this state transition diagram, right?
Uh,
Okay.
I don't think so.
Okay. Let me explain this also. So we have different processes state when the process is in running state. So here we are creating a new process. So first it goes to the ready state. So the process become ready to be handled by the processors, right? We have a different cores on our machines, and this process has to be taken by this processor. So it first comes into the ready state. So after the ready state, the scheduler will pick the process from the ready list and push the process on the running list of the processor. So when it comes to the running list, it will execute by the processors on the board, right? So when this is in the running state and we have some sleep call or we give some delay in the process, so it will, yeah, it will actually go to the waiting queue. So these are all the things.
Sorry, this is my
Oh,
daughter.
oh,
You can continue.
okay, okay. Okay, so this is a running state, and we have the sleep into the process. So when the sleep comes, it will go to the waiting queue. So this is the waiting queue. So the process will remain into this waiting queue until the sleep finishes, right? Like we have a sleep 5, so it will actually delay. The process will delay for 5 seconds, so it will actually wait on the waiting queue. And when this process actually this sleep expires, it again goes to the ready queue for the scheduler to pick it again, right? So here is actually the view. And here if the process is in the running state and if we use the kill command, like I said you earlier, it will create a signal to this process and it will go in the terminated state. So the process
Raul,
actually, yeah,
can you give me 1 minute to move
yeah,
to
sure,
another room? Okay.
sure.
Yeah. Sorry, we can continue. Uh,
Okay,
my daughter wake up
sure,
earlier.
sure, sure, sure. So when your process is in the running state of a core, then it will get terminated by using a kill command. So when we use kill hyphen 9 and the PID of a process, then it will kill this process. So hyphen 9 is for security, so we can actually have this. So this is the whole flow of how the process is being managed by the core, by the scheduler. So any doubt in this state transition
No, it
diagram?
is clear.
Okay, right. So we have different priority round robin FCSA first come first server and preemptive schedulers. So that all is a scheduler dispatcher type. So the scheduler are actually the main uh, manager for all the processes on a system. So we can have different types of scheduler on a Linux. So we'll study about this thing in a separate session. So we have this priority based scheduler, round robin, FCS, and preemptive. So these are all the type. So we have a keyboard and a event signal. So this is done, I think. So process goes through the multiple states even since creating by the OS. So we have first state as a new state, running state, waiting, ready, and terminated. So all the five states have been discussed. So, to manage the task, OS must have a clear picture of what each task is doing. So, we have the task priority also. So, there is one term called as a nice value for each process. So, it comes from minus 19 to 20 in a Linux system. So, if we decrease the nice value, then it will increase the priority of a process. So, it can be changed by using the nice uh, command, right? So task priority, so whether it is running on the CPU or blocked on some event, so what address space has been assigned to it, which files it is allowed to address, and so on. So these are all the things that actually this task management is done on OS. So usually the OS maintain a structure whose field contain all the information related to the system task. So we have one term called as a PID, that is process identification. So this process ID actually have the process descriptor. So this is actually a structure in the kernel space that is reserved for a particular process, and these are all the components of that structure. So information associated with each process, their process stage. Here we are actually saving our process state. Then we have a program counter, so it will show where the program is. Then we have some CPU registers, actually that is related to the process tasks, context switching. So these two CPU registers are being used. So CPU scheduling information, memory management information also is there in this structure. Then we have IO status information. So these are all the terms are related to the PID.
Okay.
So let's take a small example of a dot out file in process. So let's say we have one file here, and this is the PID of this API dot server. So actually, this shows it's in the terminated state, right?
Hmm.
And let's go for the section slash proc. So this is the all the files that is related to that executable that I have launched earlier. So it actually contains all the attributes of that project. Then we have the command line interface for that process. So we have all the things you see here. There is a fd folder also for file descriptor that we actually generate into our process. So fd info, map info, then we have the memory info, then we have all the things, session id, right? Then we have the stats related to that. Then we have the timer information of the process. Then we have the system call information, right? So like we
This
have,
process 293
yeah, yeah,
was created in your session, right?
yeah, I have created that process earlier. So here I have created this process. So after that I
Uh,
have use control Z and stopped it. So you can see here it is stopped, but is in a
yeah.
terminated state, right? It is in the terminated
Uh,
state, right? Yeah.
how long the terminated process stay in the proc folder?
No, no, because that is actually the cache for this process. It's not in the running state. So when
No,
we
yeah,
actually, yeah, that is a cache actually, not the running process. So let's run this process again. So I'm running this slash dot. So let's see what is the PID for this process first. So let's go for server. So here is a server, right?
yeah,
So this PID now is in the sleeping state, right?
okay,
But it is taking the same cache. Sorry. So this is a running instance of a process. So these are all the files. So it is in the running state right now, right? It
yeah,
is running on server, but it is in the sleeping state. It is actually waiting for some event to happen on the. So that's why it is showing as as positive, right?